Okay, guys, this next one has us do the Lewis structure and determine all of these properties for CO2. Again, if we're in introductory chemistry, we're going to stop at polar, nonpolar. We'll do it all if we're in general chemistry. First thing I want to do is count up my valence electrons. And I've got 2 oxygens, so 6 each. That gets me 12. I've got a carbon, so that's 4. Add it all together, and I have 16. Now what I want to do is I want to arrange the atoms on the paper as symmetrically as possible. Carbon is the first atom listed in the formula, so it goes in the middle. Carbon is typically always in the middle. Now, the next step is crucial in this case. I want to start off by drawing a single bond between each of the atoms that are to the central atom. Now I will reduce my count by those 4 electrons, 2 bonds, 4 electrons total. Now, 16 minus 4 means I have 12 valence electrons left to draw the rest of the structure and to get octets. So I'll start by doing lone pairs around everything. If I put 2 here and 2 there, I got an octet around the carbon. And I'm not going to fill in the octets around the oxygens just yet. But what I'll find is that I would, before I get to making octets with oxygen, I've already used all 12 electrons. I have no electrons left, and I do not have octets on everything. Now, I can move these lone pairs around to make octets, but as long as I try to use only single bonds, I can't get octets on everything. So what I want to do in this case is start to erase lone pairs and use those 2 electrons to make double bonds. So again, take a lone pair and use that lone pair to make a double bond. Now, what you notice is the number of electrons around as we assign them to carbon stayed the same. It has 8 around it, still has 8 around it, but also we increased oxygen by 2. And so the oxygen on the right has an octet. If we do the same thing with the lone pair, the other lone pair on carbon, and we turn it into a double bond to the oxygen on the left, then we'll get a full octet on the oxygen on the left and an octet on the carbon as well. So now we're running out. Now we have octets on everything, and we're out of electrons. That means we're done drawing the Lewis structure. Okay, so now we can determine all the geometries. Remember, a double bond counts the same as a single bond when you're counting for geometry groups or electron groups. The carbon in the middle only has 2 electron groups. It only has 2 geometry groups. I'm using the term interchangeably. A double bond to an oxygen only counts 1 time, so it has 2 geometry groups. That means the electron geometry is linear. Neither of those geometry groups are lone pairs, so our molecular geometry is still linear. And now the bond angle, of course, would have to be 180 degrees if it's linear. Now, we're going to say whether or not it's polar or nonpolar. We're going to examine the structure. The bonds are polar, but the 2 bond dipole moments cancel each other out, so it's nonpolar. In fact, we could say that the 2 geometry groups around the carbon are identical. That's another way to lead us to the idea that it's nonpolar, although that doesn't work every time. If you're in introductory chemistry, that's it for you. If you're in general chemistry, you need to figure out the rest of this stuff. So we need to go back and do the intermolecular forces. It's nonpolar. So that means there's only dispersion forces. None of the other forces would be present in a collection of these molecules. We can sort out the hybridization by going back to the geometry. A linear geometry means sp hybridization. Now, the number of sigma and pi bonds is based on the types of bonds present. We've got 2 double bonds, and in a double bond, I've got 1 sigma bond and 1 pi bond. And since I have 2 double bonds, then that means I have a total of 2 sigma bonds and 2 pi bonds. Again, each one of the double bonds contributes 1 sigma and 1 pi. So I'm getting 2 sigma total and 2 pi bonds total. And that's it for this problem. Okay, thanks, guys.